Oxidation number. So one bookkeeping rule that's used, and I'm going to preface this here by saying it's sort of a very useful bookkeeping rule that is mostly correct, but is not 100% correct. Really, electrons are shared over an entire molecule, but generally you could consider them sort of as belonging to one atom or another, especially difference in electrons from the initial state being lost from more or less one atom, more or less. So we're going to learn the rules for figuring out the bookkeeping of where the electrons are. So how do we tell the electrons are if it's not an ion? If it's Na+, that's pretty clear. But what if we're dealing with two covalent compounds in those both places? So oxidation numbers are these bookkeeping tools that tell us where the electrons mostly are. So what are the rules for this? How do we know exactly what atom sort of has ownership of that electron? So rules of oxidation numbers. So the sum of oxidation numbers is equal to the total charge of the molecule. We know that the charge of the molecule will be due to imbalance of electrons. So the total imbalance between atoms has to be equal to the total charge. So the oxidation numbers measure excess or deficits of electrons. They have to equal the total charge. We'll see examples of that soon. So that's how you know is that it's dealing with where the electrons are, so the total sum of oxidation numbers has to equal the charge. Atoms and polyatomic molecules usually, there's a lot of exceptions, but you start out by saying, unless I have other evidence, then atoms and polyatomic molecules usually has the same charge of the ion, unless it leads to result in nonsensical, and then we see, okay, which ones are more likely to have the same charges of the ion and which are less, and then give sort of the extra charge to those that are less likely to remain the same. So H is +1 unless it's with a metal like sodium or calcium. So usually just a group 1 or group 2 metal. In those cases, it's -1. In that case, the metal overrides what the hydrogen usually has. Usually hydrogen wants to give it up, but to a metal, it'll accept 1. Oxygen is -2 unless it's in a bond with itself. And then it can't give away that many electrons, then it will only have a -1 in those circumstances. So, but usually it's -2. Halogens are usually -1, except when bonded to oxygen, when you have something like a perchlorate. But if they're bonded to a carbon or nitrogen, they're going to have a -1. Okay, so let's go through and look at some examples of determining oxidation numbers. So, where's that? Yeah, okay. Actually, let's go through some examples. So O2, molecular oxygen, the total charge has to be 0. And if they're both 0, O2 is the same. You can't have +1, 1 + 1, 1 - 1. It would be symmetric. So we have just both oxygens have 0 oxidation number. Al2O3, well, this is an ionic compound. And if it's an ionic compound, then we're going to assume that the oxidation numbers are going to be the same as the ions. They're ions, so ions have an oxidation number that's equal to their charge. So oxygen is -2, aluminum is +3, and we can see they indeed add to 0 because 2 times 3 plus 3 times -2 equals 0. I mean, we know that ionic compounds are net neutral. So if the oxidation number is equal to the charge of the ion, then it's just 0. Okay, H2SO4. Now this gets a little more interesting. Clearly, if sulfur, which would usually be -2, can't be -2 here, or the numbers would just wouldn't work. They wouldn't add up to 0. So, but hydrogen is going to be +1, and oxygen is going to be -2. SO4 has this shape. The oxygens aren't bound to each other. They're bound to the sulfur. So the total charge is going to be 2 times 1 for the hydrogen plus whatever S is, plus 4 times -2, and this has to equal 0. And so we can just do algebra. We have 2 plus S minus 8 equals 0, and that leads to S equals +6. So the oxidation state of sulfur is +6 in this case, oxygen -2 plus 6, and that all adds up because 2 plus 6 is equal to 8. Okay, lithium hydride. Aha, this is lithium is going to be +1, and H is going to be -1. It's with a metal. So There we've got some straightforward cases. Let's go to some more complex ones next. So potassium permanganate. So looking at potassium permanganate, again, we would have potassium is going to be +1. Potassium is going to be +1. Oxygen is going to be -2. We don't know what the manganese is, so it's 1 plus m plus 4 times -2 equals 0. So that gives us, when we do the algebra, we get Mn, the magnesium oxidation state is +7. It's pretty highly oxidized. It's down 7 electrons from what it would usually have. Where do they go? The oxygen, essentially. Here we have something. I didn't want to draw, write just a chemical formula. I wanted to draw a chemical structure so we can look at the oxidation numbers here. Here we notice we have an OO bond. So each of these is actually -1, -1. Hydrogen's +1, +1, +1, +1. What's the carbon? Well, we don't know, but we know it has to equal 0. 4 +1s from the hydrogen +2 -1 equals 0. Is the one here. So this is C +2 equals 0. C has a -2 oxidation number here. It's electron positive. How about C2O4 minus? In this case, the atomic structure is CCOO minus. We'll learn how to draw these more, or remember how to do these more. We'll review this in a couple weeks. But that's the structure that it looks like. And so in this case, we don't know what the charge on the C is, but the O is probably going to be -2. And notice the overall charge is -2. It's not 0. So we have 2 times C, which is unknown, plus 4 times -2 is equal to -2. So that's 2C minus 8 equals -2. 2C equals 6, so C equals +3. The oxidation number of carbon is 3. It's symmetric, so they should have the same numbers. Okay, here, arsenate ion. We have, we don't know what arsenate is, yeah, but we can say that it should be, the oxygen should be -2 and the total is -3. And so therefore, the arsenic -8 equals -3. And so the arsenate has a oxidation number of +5. Because the total for the molecule has to be not 0, it's whatever the charge on that ion